I got a little upgrade to my LINQ knowledge a couple days ago. Basically, I found out about a bunch of newish stuff and figured I'd do a quick video. And here it is, LINQ methods you're not using but should be. Most developers, me included, tend to use only a handful of LINQ methods in their daily coding. But the framework offers dozens of powerful operations that can dramatically simplify your code. Today we'll explore the hidden gems that shipped with .NET 6 and later. When .NET 6 dropped in 2021, it quietly introduced a suite of new LINQ methods that solve common programming problems we've been working around for years. These aren't just syntactic sugar, they're more performant and cleaner alternatives to hand-rolled solutions. Hopefully by the time you're done with this video, you'll have some ideas for turning those 10-line loops into single LINQ calls. And then finally, I will freely acknowledge that some of the code samples that are in this video are going to be a little tough to read, especially if you're watching this on your phone. Not to worry though, the link to the code samples is in the description for this video. For a couple of these LINQ methods that I'm about to start getting into, I'm going to mention something called Big O notation. If it's been a while since you took algorithms in your CS degree, or if you have a degree in music performance like I do, well, I'm going to do a quick overview of what this whole Big O notation thing is all about. Big O notation tells us how much more work an algorithm does as our data gets bigger. It's not about exact milliseconds, it's about the growth pattern. Will doubling your data double the time, quadruple it, or something worse? We use Big O to understand what happens when things get bad, when you have thousands or millions of items. Your code might be fast with 10 items, but what happens when production has 10,000? That's what Big O helps predict. Big O doesn't care if one algorithm takes 2 milliseconds and another takes 4 milliseconds for small data. It cares whether one takes 2 seconds and the other takes 2 hours when the data is huge. It's about the shape of the curve, not the starting point. With ON algorithms, if you go from 100 to 200 items, the work goes from 100 to 200 operations. It's predictable and scales linearly. This is what we want for most operations. The work grows at the same rate as the data. With ON2, doubling from 100 to 200 items means work jumps from 10,000 to 40,000 operations. By the time you hit 1,000 items, you're doing 1,000,000 operations. This is why nested loops over the same collection are dangerous. At 10,000 items, ON might take 10 milliseconds while ON2 takes 10 seconds. At 100,000 items, ON takes 100 milliseconds, but ON2 would take 15 to 20 minutes. This is the difference between a responsive app and one that times out. Sorting algorithms like quicksort and merge sort are ON log n. This is much better than ON2, but still worse than ON. For 1,000 items, ON does 1,000 operations, while ON log n does about 10,000 operations. When you sort a collection just to get the minimum or maximum, you're doing ON log n work for an ON problem. It's like alphabetizing your entire bookshelf just to find the book that starts with A. Unnecessary work. The difference becomes dramatic at scale. Finding the max of 10,000 items with a simple scan is 10,000 comparisons. Sorting first means about 130,000 comparisons plus memory allocation for the sorted structure. That's why MinBy and MaxBy matter. Whether you're calling external APIs, sending emails, or processing database records, you often need to work with data in chunks. Most APIs have rate limits. SendGrid limits you to 1,000 emails per request. Azure Cosmos DB has RU limits, and even your own database might time out on large operations. The traditional skip and take pattern works, but it's inefficient for large collections because skip has to enumerate through all the skipped elements. For a collection of 10,000 items processed in batches of 100, the last batch requires skipping 9,900 items just to get to the final 100. Managing loop indices manually opens the door to off-by-one errors, and the code doesn't clearly express the intent of batch processing. It's also easy to accidentally modify the collection during iteration, leading to subtle bugs. Unlike skip-take, which returns enumerable that might re-enumerate, chunk returns concrete arrays. This means you get the actual count without enumeration and can safely pass batches to methods expecting arrays or ilist without triggering multiple enumerations. Chunk processes the collection exactly once, giving you ON performance compared to the ON2 behavior of repeated skip operations. For a 10,000 item collection in batches of 100, that's the difference between 10,000 operations and 500,000 operations. The code now clearly expresses what you're doing, processing in chunks. There's no index math to verify, no boundary conditions to test, and the for each loop guarantees you'll process every item exactly once. Let's be honest. We've all written that group by followed by select first pattern when we needed distinct objects by a property. It works, but it's not obvious what the code is doing, and GroupBy creates intermediate collections we don't actually need. Previously, getting distinct objects meant either implementing IEquality comparer with getHash code and equals methods, typically 20+ lines of code, or using the GroupBy workaround. Now it's just one method call with a lambda expression. When you see DistinctBy or UnionBy in code, you immediately understand what's happening. Compare that to group by followed by select first, which requires mental translation to understand the actual goal. GroupBy creates a dictionary of lists internally, allocating memory for groups we immediately throw away. DistinctBy uses a hash set internally, requiring only ON memory for the distinct keys rather than ON memory for the entire grouped collection. Here's another tweak to LINQ, plus a little bit of obvious news. If you only need to grab one item off a collection, sorting that collection just to find that one thing can sometimes be a big ol' waste of time. MinBy and MaxBy scan the collection once, keeping track of the current minimum or maximum. For a collection of 10,000 items, that's 10,000 comparisons versus 130,000 plus comparisons for a full sort, not to mention the memory allocation for the sorted structure. Unlike OrderBy, first, which throws an exception on empty collections, MinBy and MaxBy return null, eliminating the need for first or default and null checking. This matches the behavior you usually want. No items means no minimum or maximum. While Min and Max return the minimum or maximum value, MinBy and MaxBy return the actual object that has that value. You get the whole customer with the highest purchases, not just the purchase amount, saving you from a second lookup. Previously, you'd extract IDs into hash sets, perform set operations on those IDs, then filter your original collection. ExceptBy and IntersectBy do this in one pass, eliminating the intermediate collections and the secondary filtering step entirely. The beauty is that you can compare collections of different types, customers against order customer ids, products against SKU strings. As long as the key selector produces comparable values, you can perform set operations across heterogeneous collections. The returned objects are the exact same references from your original collection, preserving any additional state or lazy loaded properties. You're not creating new objects or losing data during the set operation. If your IEnumerable is actually backed by a list, array, or any I collection, TryGetNonEnumeratedCount returns the count immediately without enumeration. This is perfect for APIs that accept IEnumerable, but need to handle concrete collections efficiently. For LINQ queries, yield return methods, or database queries that haven't been materialized, it returns false, letting you know that getting the count would require full enumeration. This prevents accidentally triggering expensive database queries just to show a count. Knowing whether you can get a count cheaply lets you make smart decisions, pre-allocate arrays of the right size, show accurate progress bars, or decide whether to materialize a query. It's particularly useful in generic methods that accept IEnumerable. The new overload without a selector function automatically creates tuples, giving you clean destructuring syntax in for each loops. This is perfect for combining parallel arrays from different sources like CSV columns or API responses. Zip automatically stops when any collection runs out of elements, preventing index out-of-bounds errors. This safe default behavior means you don't need to check counts or worry about mismatched collection sizes. You can zip collections of completely different types, strings with integers, domain objects with DTOs, or test results with performance metrics. The lambda expression or tuple gives you type safety while keeping the code readable. I realize that the code sample here is pretty small and might be tough to read, especially if you're watching this on your phone. Remember, the link to the sample code is in the video description. UnionBy merges order sources while automatically handling duplicates that might exist across channels. This is common in retail, where the same order might appear in multiple systems during synchronization delays. Chunk appears twice here, once for email batches to respect API limits, and again for database transaction batches. Each batch becomes a natural unit of work that can be processed, logged, and error handled independently. ExceptBy identifies customers with no recent orders, a key business metric. Instead of complex SQL or multiple database queries, we find inactive customers with a single LINQ operation that clearly expresses the business logic. Every order, followed by first or last in your codebase, should be replaced with MinBy or MaxBy. You'll get better performance, clearer intent, and safer null handling for empty collections. DistinctBy and UnionBy eliminate the need for group by workarounds and custom equality compares. Your code becomes more readable and performs better without the overhead of creating groups you immediately discard. Whether it's API rate limits, database transactions, or parallel processing, chunks should be your go-to method for batch operations. It's more efficient than skip take and clearly expresses your intent to process in batches. These methods alone justify upgrading from older .NET versions. They're not just convenience methods, they represent years of community feedback transformed into efficient, production-ready implementations that solve real problems. Anyway, I hope you found this video entertaining or at least educational. If you're feeling wildly ambitious, please consider clicking like and subscribe. Thanks again for watching.